Hello everyone and welcome to the next lecture of the NPTEL course Machine Learning for Core Engineering Disciplines. In the last few lectures we started our journey into unsupervised learning, wherein we want to understand the underlying structures and patterns in the data without having any target variables that we would like to predict. And we first started out with our journey into principal component analysis, which was a methodology for linear dimensionality reduction. Then we changed gears and moved on to clustering algorithms, wherein we studied algorithms like k-means clustering, k-medoids clustering and density based spatial clustering of applications with noise or db-scan. And now in today's lecture we will come back to dimensionality reduction, wherein we will learn techniques such as UMAP and t-SNE, and we will understand how they work and why they are useful for nonlinear dimensionality reduction. So let us go ahead and get started. So right now we are studying unsupervised learning. And in one of the previous lectures I told you there are mainly two types of unsupervised learning algorithms. They are either clustering algorithms or they are dimensionality reduction algorithms. Right. So in clustering algorithms we looked at k-means clustering, wherein the clusters were decided based on which mean, right, of each cluster was every point closest to. And then we discussed that k-means clustering is quite sensitive to outliers because the means can be greatly skewed by the presence of certain outliers. So we looked at k-medoids clustering, right. And finally we looked at db-scan, right, which is density based spatial clustering of applications with noise. As the name suggests, this method is useful when there is noise in the data, when there are outliers, and that is because it relies on this density based approach, wherein you try to group points which are more densely packed and then separate points which are less densely packed, right. And this is the order in which these algorithms were developed in terms of when they were developed. The k-means clustering was more in the 60s, and then k-medoids clustering was more in the 1980s, and then density based clustering was more in the late 1990s. So that is how the clustering algorithms have proceeded in terms of time. Now if you come to dimensionality reduction techniques, we have already looked at linear dimensionality reduction, which was done through principal component analysis, and this is where we also studied the topic of singular value decomposition, which is the extension of eigenvalue decomposition to rectangular or non-square matrices, PCA. And PCA was really around the turn of the century in the very early 1900s. So it is a very old technique, much older compared to machine learning itself and k-means clustering and k-medoids clustering and so on and so forth. But later a lot of developments have happened in nonlinear dimensionality reduction, which is very important, right. So in terms of nonlinear dimensionality reduction we are going to learn a few concepts today, and that includes t-SNE, so T distributed stochastic neighbor embedding, that is t-SNE, and then we are going to look at UMAP, which is uniform manifold approximation and projection. These are much later algorithms. t-SNE was somewhere in the late 2000s, and then UMAP is much later, in the late 2010s is when UMAP was introduced. And of course when you talk about nonlinearity, nonlinear dimensionality reduction, you can also use the concept of autoencoders, right. And however, this is done via neural networks. So they involve neural networks, which we have not yet covered. So we will just discuss the autoencoders qualitatively, and the more mathematical aspects we will come back in the later lectures. So far we have already looked at k-means clustering, we have looked at k-medoids clustering, and we have looked at DB scan. That is with respect to clustering algorithms. And in terms of dimensionality reduction, we have already looked at principal component analysis, or PCA. So what remains to be done is t-SNE, UMAP, and a qualitative introduction into autoencoders. So let us go ahead and get started into non-linear dimensionality reduction, where we will discuss about t-SNE. So the first algorithm for today is t-SNE. So it is T distributed stochastic neighbor embedding. And this is a statistical method for nonlinear dimensionality reduction. Okay. So if you remember principal component analysis, through the use of SVD, we were just linearly combining the features, right. The new features, the principal components, right, they were in some way a linear combination of the existing features, and we even showed the way this can be implemented through matrices. But the fact of the matter is that any kind of nonlinear combination of features to obtain a lesser number of features or lesser number of dimensions is not possible through principal component analysis, and that is the reason why these more advanced algorithms have been developed, right. So this is a technique for nonlinear dimensionality reduction, which maps data in a high dimensional space let us say with p dimensions to a low dimensional space. Let us say with d dimensions. Okay, so that is what we want to do, but there is an underlying goal while we do this. It is not just that we want to reduce the number of features, we also want to do so while retaining some structure. So the goal is to preserve local similarity structure. Of the data set, so that points that are closer in the high dimensional space remain so in the low dimensional space as well. So that is the target that we want to do, so that points which are more similar to each other, which are closer to each other in the high dimensional space remain close in the low dimensional space, and that is important because you do not want to lose the underlying structure of the data set depending on whatever application you are looking at, that could be very important, right. So let us consider 2 points, right. So for 2 points denoted by xi vector and xj vector in the data matrix X, and X you know is a matrix of size n by p because there are n data points and there are p features, right. So in this scenario you can define a similarity metric. So this similarity metric essentially determines the conditional probability of xi, right, the point xi picking xj as its neighbor, right. So if you know how probable the second point is in the vicinity of the first point, then you know how similar those points are. So that is the whole logic, and you can map the conditional probability of these points being closer using sort of a Gaussian distribution, right. So we can write the conditional probability p j given I, right, as like I said a Gaussian probability which is normalized. So exponential of the norm, right, xi minus xj squared divided by 2 sigma I squared divided by sum k not equal to I. So sum over all the other points the same factor, right. So the norm of xi minus xk divided by norm squared divided by 2 sigma I squared, okay, and this is for j not equal to I. You can write this, and of course if I is j, it does not make sense too much to talk about this conditional probability, so we state it as being 0, right. So the physical meaning of this is the conditional probability of xi picking xj as a neighbor with a Gaussian chance, okay. So that is the meaning of this, and then the probability of I picking j and j picking I, right, they should be the same, and we should normalize this. So we write that as Pij equals Pji, so that is Pj given I plus Pi given j divided by 2n, right. So we have normalized this by the number of data points. Now one question to ask here, and an important one at that, is what is this sigma I, right. So what is the width or the variance that you are assuming for this particular distribution, conditional probability of a second point lying in the vicinity of the first point, and this is determined based on binary search to maintain a fixed effective number of neighbors, okay. So this is determined, these sigma ij's or sigma i's are determined by binary search to maintain a fixed effective number of neighbors, and we will give a little bit more detail about this, how this can be done. So essentially what you do is that you say that the effective number of neighbors is given by sum over the neighbors Pij. Okay, so this k is the effective number of okay. So all these are effective probabilities, right, which are exponentials, and then you take the log, so you get the number of neighbors, right. So this is how your sigma i's are computed, and this k is a parameter in the model, right. You have to specify how many effective number of neighbors there are, right. So that is what is happening in the algorithm. So this is in the high dimensional space, that is how the similarity metric is defined. Now you have to map each point is mapped to a lower dimensional space. Okay, so corresponding to xi vector you define a yi vector, corresponding to xj vector you define a yj vector, right, and we already discussed this has p dimensions, but these only have d dimensions. Okay, so that is what we had wanted. Okay. Now in this lower dimensional space you define the similarity using the student's t distribution, and that is where the name is coming from, the t-SNE or the t distributed stochastic neighbor embedding, that is coming from here. So in the lower dimensional space where y and j, yi and yj exist, a student's t distribution with 1 degree of freedom essentially that makes you have a heavier tail, which solves the crowding problem in the lower dimensional space. You do not want too many points to be very close to each other. So here you define the similarity Qij as 1 plus the norm squared yi minus yj reciprocal divided by sum over k not equal to L 1 plus the norm of yk minus yl squared to the power minus 1, right. So this is how you define the similarity metric in the lower dimensional space. And now given these the way to define similarity, we still have to find what yi and yj are, right. So to determine the points y1 y2 up to yn, remember there are yn points, right. So you minimize, right, the difference between the two distributions, the distribution, right, represented by the qij's and the distribution that is represented by the pij's, right. So you want to minimize the difference between these two probability distributions, and that is done through something known as the Kullback-Leibler divergence, the KL divergence, which you hear quite a lot in machine learning, but essentially it just quantifies the difference between two different distributions. So to determine these points, the Kullback-Leibler KL divergence is minimized between the two distributions. Okay. So, and the KL divergence between the distributions represented by P and Q, the random variables P and Q, that is sum I naught equal to j Pij log Pij divided by Qij, right, and this is minimized via the gradient descent method, which we have studied earlier in this course. Okay. So, in this way, right, you can obtain the Yij's, and thus, right, the resulting the resulting Yi's exist in a lower dimensional space thus achieving the objective of nonlinear dimensionality reduction while preserving the local structure. So, what does this mean by preserving the local structure? If you remember, we had defined the conditional probability of a second point being close to a first point, right, locally, and that is basically local structure, right. You find out what is the chance of another point lying nearby, and then you try to keep the same chance, right, in the lower dimensional space, and that is how you preserve structure, right. So, the points which are closer, they will remain closer, and the points that are farther, you typically expect them to be farther, but that is not necessarily true when you do t-SNE. So, that is why other more complex nonlinear dimensionality reduction techniques such as UMAP have been developed, right. So, that is where our discussion takes us to. So, from our discussion of t-SNE, we go on to our discussion of UMAP, which is the next nonlinear dimensionality reduction technique that we will study. So, we want to look at the uniform manifold approximation and projection. And like I said, this was very recent. I mean, the last decade is when this method has really come, and like I just alluded to a few minutes ago, the main challenge with t-SNE is that points that are far away, which is essentially what is a global structure, that may not be maintained there. So, the challenge with t-SNE is that global structure is not or may not be preserved, although local structure is. So, that is where UMAP comes in, which tries to preserve, right, both local and global structure. So, this is nonlinear dimensionality reduction preserving both local and global structure. Okay. So, how is this done, right? Let us see how this is done. So, the following are the steps in UMAP. So first, for each data point xi in the higher dimensional space, and we are dealing with real data. So there are p components, each of them are real. We find its neighbors within the k nearest ones using the Euclidean distance as a metric. Okay, so that is the distance metric. Again, just like in k means clustering, we use the Euclidean distance here. So we compute, right, dij, which is the distance between xi and xj, or the norm of xi minus xj vector, and thus we determine the following quantities. The first is the distance to the nearest neighbor, and this is used as a normalization factor in the conditional probability. So we find the distance to the nearest neighbor rho I, that is the minimum distance out of all these dij's, right, except the distance to itself. So it is the smallest distance out of all these dij's except the distance to itself. So it is the min of the set of dij's where dij is greater than 0. So that is why, that is how I am writing it. So we only take the distances that are greater than 0. So we exclude the point itself, and then we look at what is the minimum distance, right, and this is important because this rho I is used as a normalization factor in the conditional probability, as you will see, right. So then the probability right of point j around point p, sorry, point I, is defined as Pij is exponential of minus Dij minus rho I, right. So Dij is always greater than rho I, so that is why you write it here, divided by this again sigma I, which is the width of this exponential, right. And now what is this sigma I? This sigma I is obtained again by ensuring the average number of neighbors k, right. So log 2k is j equals 1 to k Pij, right, and this sigma I can thus be obtained. So sigma I lies here, so this essentially is an equation for solving for sigma I. So sigma I can thus be determined by some kind of search or optimization algorithm, right, and like I said, this k is the effective number of neighbors. Okay, and we are using log 2 because everywhere we are talking about just the neighbors, right, binary probabilities, probability of a second point being next to the first point. So that is why log 2 is being used. I hope that makes sense to you. Alright, so once you have these Pij's, obviously you have to symmetrize them, right. It should not matter whether you are looking at I versus j or j versus I. So we define the symmetric probabilities or the symmetrized are defined as capital Pij is small pij plus small pji minus pij pji. Okay, so this is how the probabilities are symmetrized, and once these probabilities are obtained, then we have to go to the lower dimensional space. So this is, as you can recall, all this is in the higher dimensional space. So if you remember what happened in t-SNE, we tried to define a similarity metric in the lower dimensional space, and then we tried to make those two similar by the use of the KL divergence. Here we will use something different, we will work with the cross entropy so that the global structure also can be maintained, right. So all that, however, will have to be done in the next lecture as we have run out of time. So thank you for joining today. I hope you learned something from the discussion of the nonlinear dimensionality reduction that we did today. We talked about the concept of t-distributed stochastic neighbor embedding, and how, unlike principal component analysis wherein the features are combined in a linear form, here you are projecting data from a higher dimensional space to a low dimensional space. So it is nonlinear dimensionality reduction, however the manner in which it is happening, you can't really sort of get as much physical insight as you got when you did principal component analysis. So that, in that sense, you get less intuition, but at least there is a way to map all the data from a higher to a low dimensional space. We also started our discussion of UMAP, uniform manifold approximation and projection, and we got down to a point wherein we defined the similarity metric, the probability distribution in the higher dimensional space. In the next class we will start from here, we will look at how the probabilities are written in the lower dimensional space, and how we can assign the points, right, yi's and yj's in the lower dimensional space. Thank you, and I look forward to seeing you next time.